You know how we're always trying to find ways to, like, grasp these big, fascinating ideas without drowning in technical stuff?
Yeah, cutting through the noise.
Exactly. Well, today we're jumping right into something really wild. Einstein crosses.
Ah, yes. Fantastic
They're
topic.
not just cool space pictures, they're uh, cosmic puzzles that tell us a surprising amount.
Absolutely. For anyone amazed by how the universe works, Einstein crosses are just, well, they're perfect examples. We're talking about gravity bending light in a very specific, very elegant way.
Light from quasars, right? These super bright, distant things.
Exactly. Quasars, these incredibly luminous cores of distant galaxies powered by supermassive black holes feeding on the surrounding material and intense radiation pouring out.
Okay, so we've got these distant quasars, and our source material today, including this great paper referencing the Gaia mission, Perryman Gaia-058.pdf, talks about how gravity messes with that light on its way here.
Precisely. Think of a massive galaxy, or even a cluster of galaxies, acting like a lens, a gravitational lens. As light from a background quasar passes by, its path gets bent by that gravity.
Gravitational lensing. Okay.
But sometimes the alignment is just right, and that bending creates multiple images of the same quasar.
Multiple images. Okay.
An Einstein cross is a specific case where you get four distinct images of that one quasar, often arranged in a cross shape around the foreground lensing galaxy. It's like a cosmic funhouse mirror effect, but, mathematically precise.
Four images of the same object.
Yeah.
That's mind-bending. So it's obviously visually stunning, but why is this four-image thing so important? What do we learn from these really rare alignments?
Well, that's the amazing part. These strongly lensed quasars, especially in Einstein crosses, pack a huge amount of information. Our sources highlight how they give us a unique handle on measuring the Hubble constant.
The expansion rate of the universe.
Exactly, measuring it at these intermediate cosmic distances, which are notoriously difficult to pin down otherwise. Think about that using bent light from billions of light years away to refine our understanding of cosmic expansion itself. It's fundamental.
That is huge, just measuring the whole expansion.
Yeah.
But I suspect there's more to it than just the Hubble constant.
Oh, absolutely. That's just scratching the surface. These systems are also incredible probes of dark matter.
How so?
By analyzing exactly how the light is bent and distorted, we can map out the distribution of all mass in that lensing galaxy, including the invisible dark matter component.
So you're using the light bending to see the invisible structure.
Kind of, yeah. It's like using these cosmic magnifying glasses to trace the scaffolding of the universe. And it gets even more detailed. We can infer things about the environment really close to the supermassive black hole's event horizon in the background quasar.
Wait, using a galaxy lens to zoom in near a black hole billions of light years away, that's... wow.
It is pretty mind-bending, isn't it? And we can learn about the quasars themselves, too.
Like what?
We can measure the size of their accretion disks, the swirling gas feeding the black hole. We can figure out the geometry, the shape, and motion of the gas in what's called the broad emission line region, where a lot of the quasar's light originates.
Okay.
We can even get clues about how fast the central black hole is spinning.
Measuring black hole spin, that sounds incredibly difficult from so far away.
It's definitely a challenge, yeah. But the subtle differences in how the light from different parts of the quasar is lensed, the time delays, it gives us the necessary clues.
Okay, so you look at tiny variations.
Mm-hmm. And stepping back to the big picture, Einstein crosses are fantastic testing grounds for Einstein's general relativity.
How?
They let us test the theory in really strong gravity regimes, these extreme environments where the predictions of GR are really pushed to their limits.
So these cosmic alignments, they're not just lucky shots, they're like
Yeah.
data gold mines.
Exactly.
Yeah.
Gold mines for cosmology, for astrophysics, for fundamental physics.
Speaking of finding them, the material mentions the very first one discovered.
Ah, yes, the famous one. QSO 2237 plus 0305. Found back in 1985 by Hukra and his team.
Okay.
This quasar has a redshift, that's Z of 1.695, which tells us it's very distant, it's light stretched by cosmic expansion.
Right, redshift means far away and further back in time.
And what's really cool is that it appears almost perfectly lined up behind a much closer spiral galaxy at a redshift of only 0.0394.
Wow, that's a huge difference. One's practically next door, cosmically speaking, compared to the other one.
Relatively speaking, yes. The quasar's light has traveled for billions of years, while the galaxy's light took only a fraction of that time.
So when I think of lensing, I often picture stretched arcs or maybe even a full circle of light, an Einstein ring.
Mhm.
Why do we get four distinct, often nearly round points of light in an Einstein cross? It feels different.
That's a really good question, and it points to something crucial. The shape of the lensing galaxy isn't a perfect sphere. If it were perfectly symmetrical, you wouldn't typically get four images like this. You'd get maybe two images, or a ring if the alignment was perfect. To get four images, the lensing galaxy's mass distribution needs to be more complex, less symmetrical. Think of it as being kind of squashed or stretched, what astronomers call a triaxial ellipsoid.
So not a ball, more like a potato.
Maybe a slightly lumpy potato, yes.
Yeah.
It's this unevenness, this asymmetry in the mass, technically called a quadrupole moment mass asymmetry, in the detailed models that acts as a more complex lens, splitting the light into those four paths.
Okay, the lumpiness makes the four images. And that also explains why they're often points, not long arcs.
Exactly. The detailed models show how that mass distribution leads to these more compact images rather than the highly stretched arcs you see in other lensing situations.
And isn't there something called the odd number theorem in lensing? Why don't we see three or five images usually? Why four?
Right, the theorem generally predicts an odd number of images, but with Einstein crosses, there's predicted to be a fifth image.
So where is it?
It's usually incredibly faint, highly demagnified, and located right smack in the middle, hidden behind the bright core of the foreground lensing galaxy.
Ah, so it's there, just lost in the glare.
Pretty much. Technically predicted, but practically invisible in most cases.
Okay, that makes sense. So the first cross was found in 85, but lensing itself was known before that.
Oh, definitely. The very first gravitationally lensed object discovered was actually a quasar 2, but it showed only two images. QSO 0957 plus 561 AB, the twin quasar.
The twin quasar.
Found back in 1979 by Walsh and collaborators, that was really the discovery that opened the floodgates. After that, more and more lensed quasars started turning up in various surveys, radio surveys like the VLA, big optical surveys like the Sloan Digital Sky Survey, infrared with WISE.
Kind of serendipitously, sometimes.
Often, yes. And of course, the Hubble Space Telescope gave us incredibly sharp views of many of these systems once they were found.
Which brings us to Gaia. ESA's mission mapping our galaxy in 3D. Now, our source mentions it's a game changer for finding Einstein crosses, even though it doesn't take pictures like Hubble does. How does that work?
It's fascinating. Gaia's main job is astrometry, measuring positions, motions, and brightnesses of stars with unbelievable precision. While it doesn't produce conventional images, its precision gives it extremely high angular resolution.
Angular resolution.
Yeah.
So it can tell things apart that are really close together in the sky.
Exactly. Even better than many ground-based telescopes in that specific regard, sometimes comparable to Hubble for certain measurements. This lets it distinguish the multiple, very closely packed images of a lensed quasar, even if they look like a single fuzzy blob from the ground.
So it can essentially detect the separation between the four images, even if it doesn't paint a pretty picture of them.
That's the key. And the Gaia Gravitational Lenses Working Group, they call themselves GRAL, has been incredibly successful using this.
Not successful.
Well, the source material indicates they've found something like 10% of all currently confirmed strongly lensed quasars. And even more impressively, 12 of the 56 known quadruply imaged quasars, the Einstein crosses, and similar systems.
Wow, 12 out of 56. That's a huge chunk from one mission group.
It really is. It's a major leap. Gaia is essentially providing the first systematic all-sky census of these things down to a certain brightness limit. Before Gaia, we kind of suspected there should be thousands more out there, and Gaia is finally letting us find them in a structured way.
Okay, so how does the Growl team actually find them in Gaia's mountain of data? It must be like looking for needles in a cosmic haystack.
They use some really clever, sophisticated methods. One major tool is machine learning.
AI.
Yep, supervised machine learning. They train algorithms on the known lensed systems, teaching the computers to spot the telltale signatures in Gaia's astrometry, the precise positions in photometry, the brightness measurements.
What kind of signatures?
Tiny discrepancies in position or brightness that suggest there isn't just one object there, but multiple closely spaced sources mimicking a single one. Little wobbles or flickers, essentially.
Makes sense. Using AI to sift through billions of data points. What else?
Another really smart technique combines Gaia's positional accuracy with light curves from other surveys.
Light curves, how brightness changes over time.
Exactly. Surveys like Catalina or the Zwicky Transient Facility, ZTF, monitor how objects change brightness. Now, if you have a lensed quasar, all its images will generally vary in brightness together, but with slight time delays because the light paths are different lengths.
Oh, like an echo.
Sort of. So if an object looks single in ZTF, but Gaia sees multiple components, and the combined light curve looks less random, less stochastic than a single quasar usually does, that's a huge flag. It suggests multiple correlated sources, a likely lens.
That's very clever, using the timing and the position. So once they have candidates, how do they know for sure it's an Einstein cross?
That's where ground-based telescopes come in for the confirmation. It's crucial. The Graal team uses big guns, Keck, Palomar, ESO's NTT, Gemini South to get spectra of the candidate images.
Spectra breaking down the light, like a fingerprint.
Precisely. If the spectra of all the candidate images are virtually identical, that's extremely strong evidence they're just multiple views of the same background quasar, lensed by a foreground galaxy.
And that confirms it.
Yes.
Yeah.
The Stern et al. Paper mentioned in our source describes how they used this method to confirm 12 new quadruply imaged quasars. They give an example, Graal J165105.2041725, a quad system at redshift 1.451.
It really is this global effort, isn't it? Space mission, ground telescope, sophisticated analysis.
Absolutely. And the Graal team isn't alone. Other research groups are also mining Gaia data, often combining it with other surveys like Pan-STARRS and using similar machine learning techniques.
Finding even more.
Yep. Our source even mentions one group finding a rare 5-image lens quasar using Gaia and Pan-STARRS data.
5 images. Okay, so lensing can get even more complicated than 4. That's wild. So with all these new discoveries pouring in, thanks to Gaia and these techniques, what happens next? What kind of science do these new Einstein crosses unlock?
It really opens the door for a lot of follow-up work across different wavelengths. One key thing, as our source notes, is photometric monitoring.
Watching how the brightness changes over time again.
Yes, but very precisely for each separate image, by measuring those tiny time delays between flickers in the different images.
Back to the Hubble constant.
Exactly. Measuring those delays very accurately gives us another way to constrain the Hubble constant in the geometry of the universe. It's a crucial cosmological probe.
So measuring the echo time tells you about the universe's expansion. Cool. What else?
High-resolution radio observations are also key. They let us zoom in on the fine details of both the quasar jets, if they exist, and the structure within the lensing galaxy itself.
And X-rays, you mentioned those earlier.
Right. X-ray observations are becoming really important. Telescopes like ESA's XMM Newton started looking at some of these new Graal quasars, like that Graal J1651041 Sen example back in July 2020.
What can X-rays show us that visible or radio light can't?
Well, X-rays probe the most energetic stuff happening right near the supermassive black hole. Normal galaxies don't emit many X-rays, so any X-rays we see from these systems almost certainly come from the quasar's core.
Right.
This gives us a chance to estimate black hole spins, even at high redshifts. We can measure the size of the superhot X-ray emitting region, maybe just a few times the size of the event horizon itself. And because lensing magnifies the signal, we can do detailed X-ray spectral analysis on these very distant objects, which would be impossible otherwise.
So the lens acts like a natural telescope amplifier for X-rays too. Amazing. Is there anything else in the follow-up toolkit?
Definitely. Another powerful technique mentioned is near-infrared integral field spectroscopy using adaptive optics.
Okay, that's a mouthful. What does it do?
Huh? Yeah. Basically combines spectroscopy getting those light fingerprints with high spatial resolution imaging, often correcting for atmospheric blur using adaptive optics. This gives you a spectrum for every point in a small patch of sky.
Like a 3D map with spectral information.
Exactly. It provides incredibly detailed information on the composition and motion of gas in both the lensing galaxy and the background quasar, which really helps refine the lensing models.
It sounds like every new Einstein cross is not just a discovery, but the start of a whole new investigation.
That's absolutely right. Each one is a unique laboratory. And with more Gaia data coming and better telescopes, we expect to find many, many more. Each discovery pushes our understanding forward.
So wrapping things up, these Einstein crosses, these incredibly precise, almost improbable alignments, they're clearly way more than just cosmic eye candy.
Far more. They are truly powerful astrophysical tools.
Letting us probe everything from the universe's expansion rate to dark matter to the physics right at the edge of supermassive black holes.
Precisely. And missions like Gaia are just revolutionizing our ability to even find these rare gems in the first place. It's a really exciting time for this field.
It really highlights that interconnectedness, doesn't it?
Hmm.
How gravity on the scale of galaxies can bend light in just the right way to unlock secrets about space, time, and matter across these vast cosmic distances.
Beautifully put. It's a perfect illustration of how the universe itself provides the tools we need to understand it.
Makes you ponder, doesn't it? How these seemingly chance alignments, these moments where everything lines up just so, can turn out to be the keyholes through which we glimpse the deepest workings of reality. Something to think about.